As we go through the rest of Chapter 3, I'm going to be switching back and forth between the PowerPoint and the Ladybug projector here because I'm trying to tape some of these lectures. I'll try and post them over the weekend so that you guys can look at them again if you want to. All right. Here, Corwin, the author of your text, I disagree with some of the things and how he presents them. This is one of the things I disagree with. The volume calculation, he says that to calculate the volume of a square or a cubic-shaped object, or something that has 3 regular dimensions that you can measure, he says it's length times width times thickness, okay? I don't know if I agree with that idea of thickness. I think the volume calculation is better depicted by this idea of volume is length times width times height, right? Not necessarily times thickness. So that if you have something that is cubic shaped, right? Something like a book or a block or a box. So we got a cube here. Not too good at drawing things in 3 dimensions, but you guys get the idea, right? So if I said that this was 2.0 centimeters, and I said that this dimension was 4.0 centimeters, and then I said the height was 3.0 centimeters, right? I would take 2 times 4, which is 8, times 3, which is 24. So I would say the volume of this box is 24, but what would the units be? Centimeters cubed, right? And that's something that you need to make sure that you remember, because if we were to say, for example, I wanted to know the surface area of this sheet of paper, right? How could I measure the surface area of this sheet of paper? Length, well, ruler, and I'd have to take the length times the width, right? So surface area is length times width. If I measure them in centimeters, right, what would be my units of surface area? Centimeters squared, right? So you have a 2-dimensional object with surface area. You have a 3-dimensional object with volume. It's like when you have x times x, that's different than x plus x. X times x is x squared. X plus x is 2x. So that's why you had to have algebra before you come to this class, so that you make sure that you understand the algebra rules. All right. So that translates nicely because when we get into the metric system, it turns out that if you have a little cube that measures 1 centimeter by 1 centimeter by 1 centimeter, so we're talking a very, very small cube, right? 1 centimeter by 1 centimeter by 1 centimeter. A centimeter is about the thickness of your thumbnail, so that's about 1 centimeter. So it's a fairly small box. That is a centimeter cubed, and that's equal to a liquid volume of 1 milliliter, right? When we take a graduated cylinder and we pour a volume of 1 milliliter into the graduated cylinder, if I took that 1 milliliter out and I put it in a box that was 1 by 1 by 1, it would fit exactly. So this is a conversion factor that you need to remember for the rest of the course. We'll be moving from one to another. The first thing that's going to translate into is density. If density is mass over volume, and we can have 2 different kinds of units for volume, then generally our units for density are either going to be grams per milliliter or grams per cubic centimeter because of that equivalency. So density units can be that or that, and they mean the same thing. So this conversion factor you're going to be using a lot in a lot of different parts of this course, so make sure that you just put that into your brain. Turns out that the metric system is pretty useful too, because if you have 1,000 of these little boxes that are 1 by 1 by 1, and you stack them all together, you have 1,000 milliliters, right? 1,000 milliliters is the same as 1 liter. So all you're doing is moving the decimal place from one place to another. So 10 by 10 by 10 is 1,000, and so there's where the equivalency comes from. Now if we're taking and we're making some conversions, and you say, all right, we've got something like 498 centimeters cubed, right? And we want to know how many inches cubed we have, right? So there's the problem. And the way that Corwin tells you to, the way that Corwin tells you to work it out is the way that you see on the PowerPoint, which is one you're multiplying it 3 times. Here's what I think is easier. If you take the 498 centimeters cubed, and we know that centimeters and inches themselves, not the cubic versions, but the centimeters and the inches are related by what equivalency? You guys remember that from your homework? How many centimeters is in an inch? I think we might have had it up here somewhere. It's 2.54, right? 1 inch is 2.54 centimeters. Well, Corwin tells you to multiply it 3 times. I think it's easier to think of it like this, right? So if you have a linear measurement like inches or centimeters, right? To make it a volume measurement, you've got to cube it. So you just take that whole thing and cube it. So what's 1 cubed? 1. And then you take 2.54 cubed. That's going to be 8 or 9 point something, a bigger number. So it's going to be a much larger number that you're going to be dividing into the 498. So remember, cubic units are different than linear units, which are also different than square units. And so you need to treat them a little bit differently. So see how Corwin has done it here? He's moved 3 instead of just cubing it. All right, there's this idea of volume by displacement. You're going to have to do some density calculations in lab. I think it's this week or next week. And you actually have to measure volume by displacement. What does that mean? You take a graduated cylinder, you put some water in it, and then you plunk the thing down in the water that you want to find the volume of, and the water goes up by that measurement. So that's easy enough to do, right? So density, since density is mass over volume, this is a lot of the calculations you're going to be doing on the next homework assignment. We look at density in some common units for things that are solid or liquid. So solid or liquid densities are always in grams per milliliter or grams per cubic centimeter. If you're talking about the density of a gas, because gases are so far apart from each other, it's grams per liter. So solids or liquids, the density is in grams per mil or grams per cubic centimeter, right? If we're talking about a gas, the density is grams per liter, right? Because solids particles are very close together, right? Liquid particles are a little farther apart, but they're still touching. Gas particles are so far apart from each other that if you took a milliliter of gas, it probably wouldn't weigh much. It might not even weigh anything that you could measure on a balance. So in gases, we have to take a much larger volume, a liter, rather than a milliliter when we're talking about the density of a gas. All right, here's some densities of common things. So, for example, ice versus water. Look at water's density. What's the density of water? According to this table here. 1 gram per mil. Okay, what's the density of ice? 0.917. So, grams per cubic centimeter or grams per mil, right? So why does ice float when you put it in water? It's less dense. Not because it's not as heavy, because mass depends on the size of the object that you have. Density doesn't depend on the size of the object. If I have a little tiny ice cube or big gigantic ice sculpture, the density of both of those pieces is still going to be 0.917 grams per milliliter, right? The density doesn't change. The size will certainly change. The mass would absolutely change. But the density is going to be the exact same of all ice. That's why icebergs float, right? Icebergs float. Even huge, gigantic icebergs will float in the ocean. Well, what would happen if I took ice and I put it in, for example, some ethyl alcohol, which has a density of 0.789? What would happen if I put ice in ethyl alcohol? It would sink to the bottom, which is kind of unusual. People say, oh, ethyl alcohol is clear. It looks like water. You put an ice cube in it, blip, it goes right down to the bottom. When I was a bartender in college, and bartending is a lot like chemistry, right? 2 parts of this, 1 part of that. You're about 150 pounds. I can give you 3 of these before I have to kick you out, right? When I was a bartender in college, we had a bar trick that was good for some tips, right? Here's a bar trick for you. Next time you're at a bar and you can make a bet with somebody, right? Here's a bar trick. Take a tall container that's glass, fill it up with something that has a high alcohol content, like Everclear or 151 rum or something like that. It has a high alcohol content, right? Fill it up completely with that stuff, and you put an ice cube, and where's the ice cube going to go? It's going to sink right to the bottom. The first time people go, wow, you can make a bet. Do you think it's going to float? Do you think it's going to sink? And they see ice float in drinks all the time. So they say, oh, it's going to float. And you put it in, you go, oh, well, there's my first $5, right? Got that one in your pocket. Then you go, watch. Now I can make the ice rise. And they'll go, wait a minute. And I'm not even going to touch the ice cube. I will make the ice cube come up to the top without touching it. How did I do that? Just add water, right? Just add some water, and as you add water, what happens? What does the water do to the density of the alcohol? It increases it. So what happens to the ice cube? Starts to float up. At one point, you can even get the ice cube kind of hang, suspended in the middle of the volume of the liquid, which is kind of cool. Right? And they go, whoa, and I go, oh, it's magic, right? See, I'm not even touching it, and the ice cube is hanging in the air, and you add a little more, and the ice cube goes up to the top. Well, they say the Great Salt Lake in Utah. What do they say about the Great Salt Lake? If you jump in the Great Salt Lake in Utah, what's going to happen to you? You float. It's pretty darn hard to sink, right? So, what must the salt do to the density of the water? Does it increase or decrease it? Think about the example I just gave you with the alcohol. It increases the density of the water, so it makes you more buoyant, makes you more likely to float. So the density of salt water, could you make a prediction about the numerical value of the density of salt water? Would it be greater than 1 or less than 1? Greater than 1, right? So you add salt to it, it's going to make it more dense, which makes your buoyancy more apparent. Also in college, I was a swimming instructor, a little different than a bartender, right? Daytime job, nighttime job. And I found when I was teaching adults how to swim, the easiest ones to teach how to swim were the really curvy ladies. They had 2 nice little flotation devices right in front. Right? The hardest ones to teach to swim, the adults, were the really buff guys, right? If they were a bodybuilder, they're like, oh, I'm tough, I'm really strong, I can learn how to swim. They jump in the pool, they sink right to the bottom like a rock, right? Why is that true? Muscles are way more dense than fat. And women, it's okay. We're supposed to be a little chunky, right? We're supposed to be able to gain weight because we're the childbearing gender of the species, right? So that's why we float so well. The big ladies, they came in to swim, they would float around like little corks, and they didn't have to expend much energy at all to get across the pool, right? You get a big bodybuilder in there, he's got to work really twice as hard or 3 times as hard as the curvy ladies to get from one side of the pool. What's that? That's right, so he can expend them, right, and work out. All right, so if I said, let's see, I think we've got an example in the PowerPoint. Here we go. All right. We know the density of water is what? 1. So what could we say about the density of liquid 1 up here? What could we say about the numerical value of the density of liquid 1? Less than 1. What could I say about the numerical value of the density of liquid 2? Greater than 1. What could I say about the numerical value of the density of solid 3? Greater than what number? Greater than water, for sure, because it's sunk. But what could I say about the density of solid 3 compared to the density of liquid 2? Is it more or less? Greater than. So it's sinking at the bottom. What could I say about the density of solid 2?
Greater than water, but less than L2.
If it was greater than water, wouldn't it be below the water? If it was less than water, wouldn't it be on top of the water? It should be the same, right? Density of solid 2 has got to be the same as water, right? Because it's right there in the interim. It's right there in the interim. It might be a smidge more than 1, but it would certainly be less than liquid 2 or solid 3. All right. I think there's a problem in the homework like that. Easy peasy. Density is mass over volume. All you got to do is divide one by the other. You can also use density as a conversion factor. If you say the density of aluminum is 2.70 grams per milliliter, well, that's not as easy to think about as if you look at it. Remember how I told you when you're thinking about these density values and the units of the density values? If you say aluminum is 2.70 grams per milliliter, I want you to start thinking of that not as a compound unit, but I want you to think of it as 2.70 grams. How many milliliters are they talking about? 1 milliliter. So now it looks more like a conversion factor, right? That you could use this. So say, for example, if I gave you a hunk of aluminum, and I knew the volume of that hunk of aluminum was 47 cubic centimeters. And I want to know how much does it weigh. I got a hunk of aluminum, and I measured it, right? It's a cube, right? I measured it, and it comes out to 47 centimeters cubed. How could I use this as a conversion factor to figure out how many grams of aluminum I have? What would I have to do with the 47 centimeters cubed first? I have to cancel it out. What could I cancel it out with? Milliliters. And it's a one-to-one relationship, right? Didn't I tell you you're going to have to use that relationship? All right, so now centimeters cancels. Now I'm going to use milliliters, and I want to go to where? Grams. You can use it just like a conversion factor. See what I mean? And then you got milliliters cancels, and you get grams. Conversely, if I said, instead of a volume of aluminum, say I got a hunk of aluminum, it's an irregularly shaped hunk of aluminum, and I say it weighs 153.7 grams, right? I know the density of aluminum is 2.70 grams per milliliter. Could I take 153.7 grams and convert that and figure out what the volume is? Using this as a conversion factor, using my 2.70 grams as a conversion factor?
Yeah.
So grams would go where? On the bottom. On the top would be milliliters, right? Where does the 1 go? Milliliters. Grams is going to be 2.70. So you can use it like a conversion factor, and either of those two mean the same thing. If you have a milliliter of the stuff, it's going to weigh 2.70 grams. If you have 2.70 grams of the stuff, it's going to take up a volume of 1 milliliter.
Can we write those on our card?
You can, or you can write this. Density is mass over volume. Mass is what? What would mass equal? Density times volume. Here's the hard one. What would volume equal? Without going through the derivation, there's the answer. This is what. Which one of these did we use on this problem? What was I solving for here? We didn't know what the volume was, so I used this formula, didn't I? Didn't I take the mass and divide it by the density? Isn't that what I did? So if you like algorithms, use algorithms. If you like them as conversion factors, use conversion factors. Conversely, what was I solving for here in this problem? I was solving for mass. Solving for mass, didn't I take density times volume? Isn't that what I did? Density times the volume? All right. So if you like algorithms, remember those 3 algorithms. A better way to do it. You will be more successful in other chemistry or physics classes if you can do it like that, using density as a conversion factor. So that's why it's super essential for you to start thinking of density 2 ways, as 2.70 grams per mil, or 1 mil is 2.70 grams, all right? And I like to show people more than one way to work out problems because everybody thinks a little bit differently, and sometimes one way clicks with one person and the other one might not with somebody else. All right, so there's some more conversions that have to do with density. And finally, we get to temperature. Now, in the book and in core, when they go through all these permutations to make conversions to Fahrenheit. All right, we don't use Fahrenheit in science. The only science people that use Fahrenheit are the weather forecasters on TV. When they say it's 105 or 106 today in Arizona, they're talking 106 Fahrenheit. If it was 106 Celsius, we'd all be vapor, right? That's not going to happen. So we don't use Fahrenheit. The 2 scales we use are mostly what? Celsius and Kelvin. So let's talk about Celsius and Kelvin in terms of what you need to know in order to be successful in this class. All right, so we got Celsius and Kelvin. All right, so if we look at those and make a comparison between the two temperature scales, right? What's the lowest temperature on the Kelvin scale? What's the very bottom of the whole temperature scale? 0 degrees Kelvin. They call that value, that 0, they call it absolute 0. And this is a theoretical idea that absolute 0 is when all molecular motion ceases. When we measure temperature of something, we're not measuring heat. It's actually impossible to measure heat. You cannot measure heat directly. You can measure temperature, but temperature is not the same as heat. Right? So absolute 0 is when all molecular motion ceases. When you add energy in the form of heat to something, what happens to the particles of that thing? They start moving faster. Okay? Absolute 0 is the temperature at which all motion stops. Nothing else is moving because it's so cold that all molecular motion ceases. Does anybody know what that temperature is on the Celsius scale, this idea of absolute 0? It's negative 273. That means that at Celsius 0, Kelvin is 273, right? So this is where water freezes. Water boils at what temperature? If we're at sea level, right? We're a little bit above sea level here, so it's a smidge below 100. But if you're at sea level, it's 100. So what must water boil at Kelvin? 273. So you can see that it's simply 273 degrees difference. That 1 degree change in Celsius is still 1 degree change in Kelvin. So the formula that you have to use to change between them is Kelvin is equal to Celsius plus 273. You will use that formula quite a bit in this class, especially when we get to gas laws, because we have to do all our calculations in gas laws. Question?
Should the Kelvin be instead of 273 should it be degrees?
Oh, I'm sorry, up here, yep. See, talking and writing sometimes messes me up. I'm always trying to think one step ahead of you guys as I'm writing and talking, right? All right, so you'll have to use this temperature, or this change frequently. Let's just practice one of those. I got a temperature of 23 degrees Celsius. What's that going to be in Kelvin? Oh, let's see, 273, 283, 293, 94, 95, 96, right? 296 Kelvin. See how it works? You just add 273 to the Celsius temperature. If I had a Kelvin temperature of 57, what's that going to be in Celsius? Well, I'd have to subtract 273, so my number's going to come out to be something negative, right?
Negative
216. All right, so it would be negative 216 degrees Celsius. And when we signify Celsius degrees, we put a little degree mark and a capital C. When you signify, bless you, Kelvin, you just put plain old capital K. Okay? I think that might be all we need for chapter 3. I believe so. Let's look at chapter 4 real quick before I send you home. There we go. Matter and energy. Here we go. All right. Whoops. We've got things that are solid, liquid, or gas. We've got all three states of matter. There is one more state of matter that is not listed. Does anybody know what that last state of matter is? Plasma. That's like if you take gas and you give it all kinds of energy and you're super duper excited, then you call it plasma. But we're not going to talk about plasma in here. All right, things that are solids are regularly packed objects, and they are in what we call generally a crystal structure. So they're going to be very tight next to each other. They're going to be arranged very orderly. Solids are very orderly. Liquids, on the other hand, they're still touching each other, but now they're not arranged so orderly. They're going to be a little bit further apart from each other than the solids are, but they're not going to be arranged in a nice orderly structure like solids are. Gases, on the other hand, they're really far apart from each other, right? All right, so solids, when you start with solids, we have what we call vibrational motion. The particles of the solid can simply vibrate back and forth around a fixed point. So they can only vibrate. If you add more and more energy to them, what happens to the speed of their vibrations? They start to speed up even more and more and more until they speed up so much that they add a mode of motion. Here, liquids have vibrational plus rotational motion. So you add energy. So here we're adding energy when we go from solids to liquid. We add energy in the form of heat. I heat stuff up. Now it's vibrating, but now it's also rotating. So you're going like this, but then you're also rotating. So they're vibrating and they're rotating in a liquid and they're moving around. They're still touching each other, but they're a little bit farther apart. Finally, when you get to gases, then they're really far apart. We have vibrational plus rotational plus what we call translational movement. That means they're going from one place to another, a translation. So gases have the most energy of all because they have three what we call modes of motion: vibrational, rotational, and translational. They move from one place to another. Have to add energy to go from one place to another. So what's this change called? Solid to liquid, what do we call that change? Melting. Right? Liquid to gas, what do we call that change? Evaporation. That's, if we put a beaker of water in Arizona in July outside, it would sure evaporate. But what would we call it if it's done, say, on a hot plate? Vaporization is a better term than evaporation. Evaporation implies that there wasn't necessarily heat added. All right, vaporization going back to a liquid, what do we call that? Condensation. And we go from a liquid back to a solid, what do we call that? You can call it freezing. All right, there is a change that you can go directly and skip the solid phase or the liquid phase altogether. You can go directly from a solid to a gas. What's that called when we skip the liquid phase altogether? Sublimation. And what's it called when we go from a gas directly back to a solid? What's the name of that thing? Does anybody remember that one? Deposition. All right, everyday examples of sublimation. Can anybody tell me an everyday example where you might have seen sublimation occur? You buy this stuff at the grocery store on Halloween. Liquid nitrogen, yeah. Dry ice, right? What's dry ice made out of? Well, no, it's a solid. What kind of solid is it? Carbon dioxide. Yeah. CO2 gas. You know, you can make, I used to do, when I taught high school, we used to do a chemistry magic show in October. And you can make George Washington on a quarter scream with dry ice. You take George Washington on the quarter, and you put his face down on a hunk of dry ice, and then you hold it with your thumb, and it'll go, George Washington will scream. How did I make George Washington scream by holding him on a piece of dry ice with my thumb?
Because the vapor cannon.
The vapor cannon escaped, but what's my thumb at? Pressure, but what else? Heat, right? As I add heat, it's changing from a solid directly to a gas, and if I'm holding that down and I'm smooshing poor George onto the dry ice, the gas can't escape, so it vibrates the quarter really rapidly, and it sounds like George's scream. See, you learn bar tricks in here, all kinds of good stuff. All right, you can start on homework 4 now, too. Covered some of the stuff in homework 4, and I would suggest that we start that right away. The bookstore has them, but I don't know if the bookstore's closed. Home Depot or those kind of places have goggles, too.
No,
don't
we
know.
did not do the last one.